For more than a century, railways have relied on just two technologies. Either trains burned diesel fuel, or they drew electricity from overhead power lines. Now, that is beginning to change. India is preparing to introduce Asia's first hydrogen-powered passenger train, marking a significant milestone in the evolution of rail transportation. But this story is much bigger than one train. It represents the emergence of an entirely new railway ecosystem, one built around hydrogen production, storage, distribution, and clean propulsion. Today, we'll uncover the hidden engineering behind this transformation and explore why many experts believe hydrogen could become the third major power source for railways around the world. The world's railway systems are under increasing pressure to reduce emissions, while continuing to move millions of passengers and billions of tons of freight every year. Diesel locomotives remain reliable, but they produce greenhouse gases and air pollution. Electrified railways offer cleaner operation, yet installing overhead power systems across thousands of kilometers of track is expensive and often impractical. Hydrogen introduces a third path. Instead of replacing entire rail networks, operators can deploy hydrogen-powered trains on existing tracks while dramatically reducing emissions. For countries with large non-electrified rail networks, this creates an opportunity to modernize transportation without rebuilding the entire railway infrastructure. Diesel has powered railways for generations because it delivers high energy density, long operating range, and dependable performance. But it also comes with major environmental costs. Every journey releases carbon dioxide, nitrogen oxides, and particulate matter into the atmosphere. Diesel engines are noisy, require regular maintenance, and depend on fossil fuel supply chains that fluctuate with global energy markets. As governments introduce stricter emissions regulations and commit to net zero targets, railway operators are searching for cleaner alternatives that can provide the same operational flexibility without the environmental impact. Hydrogen is emerging as one of the strongest candidates. Unlike diesel, hydrogen does not release carbon dioxide when used inside a fuel cell. Instead, hydrogen reacts with oxygen to produce electricity, with water as the primary byproduct. That electricity powers electric traction motors, giving hydrogen trains many of the advantages of battery electric vehicles while avoiding the need for large battery packs. Even more importantly, hydrogen can be produced using renewable electricity, creating the possibility of an almost completely carbon-free transportation system. Instead of simply replacing diesel fuel, hydrogen changes the entire energy architecture of rail transportation. The true advantage of hydrogen is not the train itself, it's the infrastructure behind it. Existing rail corridors can be upgraded by adding hydrogen production plants, compression systems, storage terminals, and refueling depots instead of installing continuous overhead electrical wires across every route. This creates a flexible network capable of serving regional passenger services, freight operations, and remote railway lines that would otherwise be difficult or uneconomical to electrify. In many ways, hydrogen rail is not just another train technology. It is the beginning of a new industrial ecosystem where renewable electricity, hydrogen production, transportation, and railway operations all become part of one integrated engineering system. At first glance, a hydrogen-powered train looks much like any modern passenger train. But beneath its streamlined exterior lies an entirely different propulsion system. Instead of a large diesel engine connected to a mechanical transmission, this train is built around an electric drivetrain. Hydrogen stored onboard becomes the energy source, replacing diesel fuel altogether. The train combines high-pressure hydrogen tanks, fuel cell stacks, power electronics, electric traction motors, batteries, cooling systems, and sophisticated control software into one integrated machine. Every component has a specific role, working together to convert hydrogen into smooth, efficient electric propulsion. Understanding these systems is the key to understanding why hydrogen rail is attracting so much attention worldwide. The fuel cell stack is the heart of the hydrogen train. This is where hydrogen gas is converted directly into electricity without combustion. Hydrogen enters one side of the fuel cell, while oxygen from the surrounding air enters the other. Inside each individual cell, hydrogen molecules separate into protons and electrons. The electrons travel through an external electrical circuit, generating usable electric power, while the protons move through a specialized membrane before combining with oxygen to produce water. Hundreds of these cells are stacked together to generate enough electricity to power an entire passenger train. Unlike an internal combustion engine with hundreds of moving parts, the fuel cell produces electricity quietly, efficiently, and with remarkably low vibration. Producing electricity is only possible if the train can safely carry enough hydrogen for long-distance operation. That is the job of the onboard storage system. Hydrogen is compressed to very high pressure and stored inside advanced composite cylinders designed specifically for transportation. These lightweight tanks are built from multiple protective layers that provide exceptional strength while minimizing weight. Each tank is continuously monitored by pressure sensors, temperature sensors, and automated safety systems. Sophisticated valves regulate hydrogen flow into the fuel cell stack, ensuring that the correct amount of fuel is delivered under every operating condition. The entire storage system is engineered with multiple layers of redundancy so that safety remains the highest priority throughout every journey. The electricity produced by the fuel cell stack cannot drive the wheels directly. It first passes through advanced power electronics that manage voltage, current, and energy distribution throughout the train. Intelligent converters transform the electrical output into the precise form required by the traction motors. These electric motors then convert electrical energy into mechanical rotation, driving the train smoothly along the tracks. Auxiliary batteries also play an important role by absorbing energy recovered during braking and supplying additional power during acceleration. The result is an integrated electric propulsion system that delivers rapid acceleration, high efficiency, and quiet operation, while reducing mechanical complexity compared with traditional diesel locomotives. Every high-performance energy system generates heat, and hydrogen trains are no exception. Dedicated thermal management systems circulate coolant throughout the fuel cell stack and power electronics to maintain ideal operating temperatures. Heat exchangers and cooling modules remove excess heat, ensuring maximum efficiency and long equipment life. As hydrogen combines with oxygen inside the fuel cell, the primary byproduct is water. Instead of emitting smoke, soot, or carbon dioxide, the train releases water and warm air. This clean exhaust is one of hydrogen's most visible environmental advantages. Combined with the quiet operation of electric traction motors, it creates a transportation system that is not only cleaner but also more comfortable for passengers and communities located along railway corridors. A hydrogen train is only as useful as the infrastructure that supports it. Unlike diesel, which has benefited from more than a century of fuel distribution, hydrogen requires an entirely new refueling ecosystem. The hydrogen refueling depot becomes the railway's energy hub. Here, hydrogen is received, stored, compressed, monitored, and transferred safely into the train. Multiple high-pressure storage vessels feed dispensing equipment capable of delivering hydrogen quickly while maintaining strict temperature and pressure limits. Digital monitoring systems continuously supervise every stage of the refueling process. For passengers, refueling happens behind the scenes, but for railway operators, this depot is as important as the train itself. Without it, hydrogen rail simply cannot operate. Before hydrogen reaches the railway, it first has to be produced. Increasingly, that production begins with renewable electricity generated by wind farms and solar power plants. Electricity flows into electrolyzers, machines that split water into hydrogen and oxygen using electrical energy. The oxygen can be released or captured for industrial use, while the hydrogen becomes a clean energy carrier ready for storage and transportation. If renewable electricity powers the electrolyzer, the result is what is commonly known as green hydrogen. This allows the railway to move away from fossil fuels and toward a cleaner energy cycle. In many future railway systems, the fuel itself may be produced only a few kilometers away from the trains that use it. Freshly produced hydrogen occupies a large volume, making it impractical for transportation in its natural state. The next step is compression. Powerful industrial compressors increase the hydrogen pressure to hundreds of bar before transferring it into specialized storage vessels. These compression systems are among the most critical pieces of the hydrogen supply chain because they determine how efficiently hydrogen can be stored, transported, and dispensed. Sophisticated instrumentation constantly monitors pressure, temperature, vibration, and flow rates to ensure reliable operation. Although passengers rarely see this equipment, these compressors form the invisible bridge between hydrogen production plants and the railway network itself. Once compressed, hydrogen must reach railway depots safely and efficiently. Depending on location, hydrogen can travel by dedicated pipelines, road tankers, or specialized trailers designed for high-pressure gas transport. Each delivery becomes part of a coordinated logistics network connecting production facilities, storage terminals, transportation systems, and railway depots. Digital scheduling systems ensure hydrogen arrives before trains require refueling, while minimizing transportation costs and maintaining supply reliability. This logistics network transforms hydrogen from a locally produced gas into a national transportation fuel, capable of supporting large railway fleets across multiple regions. Operating hydrogen trains requires a new generation of maintenance facilities specifically designed for fuel cell technology. Instead of servicing diesel engines, technicians inspect fuel cell stacks, hydrogen storage systems, power electronics, electric traction motors, batteries, cooling systems, and digital control equipment. Predictive maintenance software continuously monitors system health, identifying potential issues before failures occur. Every major component communicates operational data back to maintenance teams, allowing repairs to be scheduled proactively rather than reactively. This data-driven approach reduces downtime, improves reliability, and extends equipment life. In many ways, maintaining a hydrogen train resembles maintaining a sophisticated power plant on wheels rather than a conventional locomotive. Modern hydrogen railways are powered by more than hydrogen, they're powered by data. Every hydrogen train continuously communicates with a central operations center, transmitting thousands of data points every second. Operators monitor hydrogen pressure, fuel cell performance, battery charge levels, traction motor temperatures, cooling systems, train location, and overall system health in real time. Advanced software analyzes this information to optimize energy consumption, predict maintenance needs, and improve operational efficiency. If a component begins operating outside its normal range, engineers receive immediate alerts, allowing problems to be addressed before they affect service. In the future, artificial intelligence will make these control centers even smarter, transforming hydrogen rail into one of the most digitally connected transportation systems ever built. Hydrogen is often misunderstood, but modern hydrogen railway systems are designed with multiple layers of protection. Safety begins with continuous hydrogen leak detection throughout the train and refueling infrastructure. Highly sensitive sensors can detect even extremely small concentrations of hydrogen, automatically triggering alarms and safety procedures long before dangerous conditions develop. Automatic isolation valves immediately stop hydrogen flow if abnormal pressure or temperature is detected. Ventilation systems safely disperse any released hydrogen, while redundant monitoring systems ensure that no single equipment failure compromises safety. Every major component, from storage tanks to pipelines, is designed to meet rigorous international engineering standards. Rather than relying on one safety feature, hydrogen railways depend on overlapping systems that work together to keep passengers, operators, and maintenance personnel safe. When comparing hydrogen with diesel, the differences extend far beyond emissions. Diesel locomotives rely on internal combustion, producing carbon dioxide, nitrogen oxides, particulate matter, vibration, and significant engine noise. Hydrogen fuel cell trains replace combustion with electrochemical energy conversion, producing electricity quietly and efficiently while emitting only water at the point of use. Electric traction motors also reduce mechanical complexity, improving passenger comfort through smoother acceleration and quieter operation. While diesel infrastructure is already widespread and fuel costs remain relatively predictable, hydrogen offers the possibility of dramatically reducing long-term emissions while integrating directly with renewable electricity. The transition will require investment, but it also creates an opportunity to redesign rail transportation for a lower carbon future. Hydrogen is not intended to replace every battery-powered train. Instead, both technologies solve different transportation challenges. Battery electric trains perform exceptionally well on shorter routes, where charging infrastructure is readily available and frequent charging opportunities exist. Hydrogen trains, however, become increasingly attractive on long-distance regional services, remote railway corridors, and routes where installing overhead electrification or extensive charging infrastructure would be prohibitively expensive. By carrying their own energy on board, hydrogen trains can travel longer distances while maintaining fast refueling times. Rather than competing directly, batteries and hydrogen are likely to complement one another, with each technology serving the railway applications where it delivers the greatest operational advantage. India's hydrogen train is not an isolated experiment. Around the world, governments and railway operators are investing heavily in hydrogen-powered transportation. Germany has already demonstrated commercial hydrogen passenger services, while projects are expanding across Europe, China, Japan, South Korea, and other regions exploring cleaner alternatives to diesel. Every successful deployment strengthens supply chains, improves manufacturing experience, reduces equipment costs, and accelerates technology development. As more countries invest in hydrogen production and railway infrastructure, the technology continues to mature. What began as a series of pilot demonstrations is steadily evolving into a global transformation of rail transportation, laying the foundation for cleaner and more sustainable railway networks throughout the decades ahead. India operates one of the world's largest railway networks, carrying millions of passengers and enormous volumes of freight every single day. While many major routes have already been electrified, thousands of kilometers of railway still depend on diesel locomotives. Hydrogen offers India another pathway toward cleaner transportation, without requiring every remaining railway line to be equipped with overhead electrical infrastructure. At the same time, the country is investing heavily in renewable energy, electrolyzers, and green hydrogen production through its broader hydrogen strategy. These investments are not just about building one hydrogen train, they are about creating an entirely new industrial value chain that connects renewable electricity, hydrogen production, manufacturing, transportation, and railway operations. If successful, India could become not only a major user of hydrogen rail technology, but also a global supplier of hydrogen engineering expertise and equipment. Despite its enormous potential, hydrogen still faces one critical challenge: cost. Producing green hydrogen requires large amounts of renewable electricity, advanced electrolyzers, high-pressure compressors, storage systems, transportation infrastructure, and specialized refueling depots. Every one of these systems adds to the total cost of delivering hydrogen to the railway. The good news is that history shows what happens when industries scale. Solar panels, wind turbines, lithium-ion batteries, and electric vehicles all became dramatically cheaper as manufacturing expanded and technology improved. Hydrogen is expected to follow a similar path. Larger electrolyzer factories, cheaper renewable electricity, improved compression technology, and growing global demand could steadily reduce production costs over the coming decade. For hydrogen rail, affordability, not engineering, is now the biggest obstacle to widespread adoption. Imagine looking at a railway map 20 years from now. Instead of isolated hydrogen projects, entire regions could be connected by integrated hydrogen corridors. Renewable energy plants generate electricity. Electrolyzers convert water into hydrogen. Compression terminals prepare it for transport. Pipelines and delivery vehicles distribute it to strategically located refueling depots. Hydrogen trains move passengers and freight, while digital control centers coordinate every stage of the journey. Every part of this network works together as one interconnected engineering system. The train may be the most visible part, but it is only one component of a much larger energy ecosystem. This systems-level thinking is what makes hydrogen rail fundamentally different from simply replacing one locomotive with another. India's first hydrogen passenger train is only the beginning. The long-term vision extends far beyond a single demonstration project. Future railway systems could combine renewable power generation, large-scale hydrogen production, smart digital monitoring, predictive maintenance, and autonomous operational control into one integrated transportation network. Hydrogen trains may eventually operate alongside battery electric trains, conventional electrified railways, and even freight corridors optimized specifically for hydrogen logistics. As costs continue to fall and infrastructure expands, hydrogen could become an increasingly important part of the global transportation mix. The pace of that transition will depend on continued engineering innovation, supportive policies, and investment in the infrastructure that makes hydrogen practical at scale. India's first hydrogen passenger train represents far more than a new locomotive. It signals the beginning of a much larger transformation in how railways may produce, store, distribute, and use energy in the decades ahead. Behind every hydrogen-powered journey lies an invisible network of electrolyzers, compressors, storage terminals, refueling depots, digital monitoring systems, safety technologies, and renewable power generation. Together, these systems create a new model for clean transportation, one designed not only to reduce emissions, but also to reshape the relationship between energy and mobility. Whether hydrogen ultimately becomes the dominant solution or one part of a broader mix of clean technologies, its influence on railway engineering is already beginning to grow. Understanding these hidden systems helps us see that the future of transportation is not defined by a single train, but by the entire infrastructure that makes it possible. If you enjoyed exploring the engineering behind India's first hydrogen train, subscribe for more deep dives into the hidden systems powering the global energy transition. At ReneEnergy, we go beyond the headlines to uncover the engineering, infrastructure, and technologies shaping the future of our world.